let's get that going. Okay, so Unit 5, jumping into today, is kind of a shorter unit. In terms of correlation to your textbook, it's only one chapter. When most other units we've done have been like 2 or 3 chapters in one unit. It's quite extensive, which I'm glad it's just one unit to focus on. But it is nice because it really is one overarching theme that try to kind of connect everything back to, right? The more you can connect chemistry, the simpler it becomes. If you just try to keep it as all these separate days, there's way too many days to try to keep track of, okay? So what Unit 5 is all about is it's all about this thing known as reaction rates and rate laws. In a sense, we're studying here. Let me back up this PowerPoint. The speed at which reactions happen. That's what a rate is. So in our lives, you can measure the rate of your car in what units? Miles per hour, right?
Per hour.
Okay, so speed is similar to rate. In chemistry, with molecules, what we're measuring here is we're measuring molarity per second. So how quickly are the moles changing every second? Now, when we look at a chemical reaction, there's 2 ways you could look at the rate, or the 2 ways you could measure it. Because some things are disappearing, while other things are appearing, right? So for example, and I apologize, I probably shouldn't even put this image on your notes, because since it's in black and white, it's like,
Oh, yeah.
you know, can't even tell. Or if you're colorblind, I'm sorry. Okay, but this reaction is just to show you A changing into B. Okay, where A is red, B is blue. Okay, the rate would measure how quickly A goes away or how quickly B is showing up. Okay, and that measures rate. One of the fundamental things in this unit that I will try to repeat as often as possible is rate is determined experimentally. It's the only way to know how fast a reaction goes. You could just think of it as same thing with speed, right? You could look at a person and try to guess how fast they are, but you really don't know how fast someone is until they go and run, right?
That's my best one. Do it right now.
Your best mile?
Yeah.
I don't want to offend you.
No, I'm totally fine. Because I'm very comfortable with my fastest
Okay.
mile. You
could run 7:05.
I actually ran a 6:30 once.
Okay, now you guess mine.
Oh, let's see.
5:20.
5:20, yeah, 5:20, 5:30.
I guess it depends on if you're talking about today or my lifetime.
Yeah, mine was my lifetime.
Yours was lifetime? Okay.
I could run like a 7.5 right now, probably. I don't know. Probably like in between 5 and 6, somewhere in there. 5:30, 5:20.
4:48.
Whoa!
Don't ask me to do that today, though. But the same idea is with chemical reactions, okay? You can't look at this and say how fast A is going to change to B. You have to do an experiment. Now, something that sometimes gets lost in this unit is a lot of times what we'll look at is we'll look at data from someone else's experiment because we just don't have chemicals or time to do experiments every day. Or same thing, the AP test is going to give you data. But it's important to go back to the fact that, okay, this came from data of them doing the experiment, okay? Now, a rate is molarity per second. So the chemical setup, or the chemical equation for the appearance of B should show the change in B versus change in time. Now, symbolically, we can represent change by using this Greek symbol right here called delta. Pretty much looks like a triangle. Okay? So I'm going to have the change in B. That's what this means. Okay, yep. Should be familiar. And if you have it, you'll learn about it sometime in math. You'll see delta all the time. Over change in time. Okay, so once again, in word terms, this means change in time. This means change in concentration. Brackets mean concentration, so the molarity of it. Now in terms of our equation of A changing into B, B is being made. So we're measuring how quickly is B being made. You can also measure it as how quickly A is going away. So we could also say the change in A over change in time, with a slight difference of having a negative with this one. The negative is important to recognize here and what it means mathematically. Is it, maybe it's a bad question to ask this class because you guys always find ways around my questions, but is there a way to go negative 10 miles per hour?
Yeah.
Drive back.
Technically, no.
Right? You can't go a negative rate. So what would a negative refer to in this case? Why would I have a negative associated with a rate? What would it be telling me, Evan?
Does it mean decreases?
Yeah, it's just like the direction, right? So this is saying that it is disappearing or decreasing.
If you're pushing on your brakes at a certain amount, your velocity is changing by -10.
But velocity isn't speed.
But they're associated. So in a way, you are going
Negative 10 miles per hour?
not negative 10. You know?
I guess in the sense of this, where you're talking about direction, right? Because velocity is like a directional thing too, right? So,
Yeah.
but notice that in this case, they're equal to each other because our example equation is a 1-to-1 ratio, right? So every single red of A was turning to 1 of B. If it's not a 1-to-1 ratio, then we are going to have a few more numbers in to make them equal. So let's look at an example of that problem, or what it could look like. Oh, I guess we'll fill in these blanks. So the rate of change of the reactant product is determined by the stoichiometry of the balanced equation. So the rate comes from an experiment, but once you have some data, you can always use a balanced equation to compare it to something else. Okay, so for example, let's look at the equation now where it's not a 1-to-1 ratio. So in this reaction, it's a 2-to-1 ratio. So what we would get here is for the rate, we still have change in concentration. So I have the change in HI over change in time. But to set that equal to the products, it's going to be cut in half because it's a 2-to-1 ratio. So what we get is that 1/2 this is going to equal the change in H2 over the change in time, or you could do it for the other one. So all those three would be equal.
I don't know if you can see the third one.
Oh shoot, the circle.
No, you can't.
Yeah, it's just right.
It's
on-
just
right
just
in the middle
circle,
of that.
circle the third one,
And then that would
yeah.
be my circle for the day.
Yeah,
Okay.
perfect.
Yeah, let's try that again. Thank you for catching that.
The equal sign is the right side of the circle.
This,
Yeah.
It's
so it goes
the
a little wider than I drew it.
Yeah.
Yeah.
Is that pretty
There
safe?
you go.
Okay, thank you. Good catch. Now, what I would probably draw to remind myself for later is I would make a note that saying, okay, this 1/2 is here because of that 2 in the balanced equation. Because 2 moles of HI disappear for every 1 mole of H2. The disappearance of HI is half the rate of appearance of H2 or I2. So this is a way in which we can compare. If I know how quickly one thing is disappearing, I can use this setup to figure out how quickly something else would be reappearing, whether it's a 1-to-1 ratio or 1-to-2 ratio or whatever it might be. Okay, so let's look at an example problem of what it could look like for solving. Okay. Oh, generic setup. Oh, I forgot something though. Add a negative here. Because since that's my reactant, it should show the disappearance, which means it's negative. Okay, so here's kind of a generic equation. Just so you know, this equation is not on your formula sheet, but hopefully you'll recognize that it's pretty much you just take the coefficient and turn it to a fraction. That's where they're coming from, but there's kind of a generic form if that helps. Ooh. Okay, so let's take a look at this problem here. That did not work. Okay, how is the rate of disappearance of ozone related to the rate of the appearance of oxygen? Okay, so from some data we found, or someone found for us, that the rate of appearance of O2 is 6.0 times 10 to the negative 5 molarity per second. What is the value for the rate of disappearance of O3 at this same time? So first step when you're dealing with rate comparisons is to set up the equation that compares the two. So here's my balanced equation. So the number right there becomes a fraction, so we're going to get 1/2. Did it go in?
It's a cycle.
Oh, darn, it's like-
You almost
You
did
can
that.
recycle.
I need to get more colors. I'm down to not very many. Okay, so we have 1/2 change in concentration of O3 over change in time, and that's going to be negative, is equal to 1/3 the change in concentration of O2 over change in time. So that's just my setup of setting it equal to one another. Questions on the setup? Okay, now the problem tells us the appearance of O2 is this right here. Now what can often be kind of like overwhelming is just the number of variables and symbols in these problems. But what you need to recognize is that this entire thing as a whole is that number. Because that is the rate. Okay, and then this whole thing right here is what I'm trying to find. So what I'm going to do to simplify it is I'm going to plug in what I know, and then I'm just going to change this to the capital R, just so it looks simpler to work with, okay? So I'm going to have negative 1/2 R, which is the rate of O3, okay, is equal to 1/3 times 6.0 times 10 to the negative 5. Got my units there. Molarity per second. Questions from here to here? Yeah, Evan.
What is that number on the far right? The 6.0 times 10 to the negative 5?
This.
Oh,
this-
that's up there. Okay, no.
Yeah, you're
sorry.
good. So this is the rate of O2, which was found experimentally, so has to be in the problem.
Okay.
Any other questions? Okay, now just do algebra. How do I get R by itself? Good, so you either could, in a sense, divide by negative 1/2 or times by negative 2. Okay, so plug that in. So I get that the rate of O3, should we plug that in correctly? I got 4.0 times 10 to the negative 5. Oh, thank you. Negative 4.0 times 10 to the negative 5 molarity per second. Yeah, Gavin.
Would you multiply multiply the 1/3 in the 6.0 before you multiply by the -2?
Since it's all multiplying, it wouldn't really matter. You should get the same answer
Okay.
either way. So,
Okay.
yeah, good question though. Yeah, Kimberly.
So I thought rate was never expressed with a negative number.
It's expressed with a negative, but it's not that it means like, how do I put it, like mathematically it's not negative, but it is, you put the negative just to show the direction. Now you are right in a sense, since I'm talking about, like I'm labeling what it is, that it is O3, it's actually not necessary to put the negative, because since O3 is the reactant, I know that it's disappearing, but does that make sense? Yeah, good question. Any other questions? Yeah, Max?
Which one would the AP grading people rather have you put? It doesn't matter.
Like the negative or not the negative? I would say for rate, you don't normally need it, because since you're like, it's specifying what you're finding, like in this case it says find the rate of disappearance. The rate of disappearance is always negative, so it's not necessary to put it. But I don't think like you'd be marked wrong for putting it. But I don't think any other problems I've seen dock you for not putting it. So, good question. Any other questions? Okay, let's step away from the math side for a second and get to, so that's kind of some symbolic side of like what a rate is of molarity per second. Once again, think of it like the speed limit for a reaction, okay? What we're gonna look at now is what are some things we can do that can affect this rate. So what are some factors that can control how quickly or how slowly a reaction proceeds? The thing that we need to understand as we look at these different factors is what is known as collision theory. Collision theory describes how and why reactions are successful. What's important to recognize is that just because two molecules collide with each other, okay, let me back up and first say this first. So in order for a reaction to happen, molecules have to collide, okay? Atoms don't react if they don't ever touch. Now when we say touch, we're thinking molecular level touch, right? Like they have to hit each other. But just because they do hit each other doesn't make them react. Otherwise, every time I give someone a high five, we'd like react with each other because we collide, right? Sorry, I guess you don't give high fives during these times. You want hand sanitizer. So not all collisions are successful. And honestly, majority are not, right? In the air right now, there's lots of different things. There's water, oxygen, nitrogen, carbon dioxide, hydrogen, other things. And they're probably hitting each other. It's not like we see like fireworks going off in here, right? Maybe.
Well, it would probably get pretty old after a while.
After a while, we just like always have
It would be your
fireworks.
whole life, just like pop, pop, pop. That'd get pretty annoying.
If we could change it though for a moment, it would be cool, right? So there's two things that are necessary to make a collision successful. Number one is the energy. If they don't have enough energy, it's just bumper cars, right? They bounce off each other, okay? Second thing is they have to collide in such a way that it bonds where it needs to bond, okay? And then the third factor, of course, is even like, do they even need to bond in the first place, right? Like, do they need to react to get a stable configuration? But what I mean by location is, let's say hypothetically here, just so you can have a visual, use these, okay? So let's say water's gonna bond with this hydrogen in this molecule, okay?
Oh, I thought that was a projection.
Did your eyes trip you there? So if these collide, so the H is trying to bond with the oxygen, okay? But if these collide like this, that's not a successful collision, right? So there's like 99 ways to collide the wrong way, and nothing happens. The only way it actually sticks is if it hits the right spot. That's why majority of collisions are unsuccessful. It's because if you think of the probability of these things flying around in space and having to hit with enough energy in the right way, it's pretty crazy, okay? So as we talk about these things, think about the molecular view, right? How does this help the reactions be more successful? So the first thing that we can do is we can change the physical state of things, right? Simple example, solid, liquid, gas. Turn to your table buddy and have a quick discussion of why would a gas typically be faster at reacting than a solid or liquid. Ready, set, go.
Well,
Isaac, you don't have a button.
Yeah.
Carly, Kimberly, can Isaac like sneak in with your conversation? Is that okay?
We're still moving on. It's the slowest there. If it even right. You can't just like put two dots together. That's maybe magnet.
Okay,
That's
anyone willing to
magnet.
share for a smiley face? Zach was here.
Because they're moving faster, so they have more chance of hitting.
Yeah. More chance of it, they're moving faster, so they have enough energy, right? That's why gases are typically the most reactive things. That's why we have to, keep them safe and stuff, because they react. Versus solids, it's pretty rare for a solid to react, or if it does, it just doesn't happen very quickly, okay? Now, I'm going to show you a reaction with lycopodium powder in two different forms, okay? What I want you to notice is what is changing and why would that make it go faster, okay? Okay, Aaron, will you just, for those that can't see this warning label, what does this say right here?
Flammable.
yeah.
Okay,
How do you get your hands on it?
so we're going to test the reaction rate of how flammable this stuff is, right?
Whoa.
That's what you do under safe conditions, right?
I
Okay,
love this class.
Yeah, this is why we all
don't do this at home. Okay, so
I
I'm
don't
going
exactly have this stuff.
I know. It's easy for me to say that.
Yeah, what is? Do you just have random chemicals in your kitchen?
In my kitchen?
Well, yeah.
Because I can?
Well, you're a chemistry teacher, so.
No, I keep most of my chemicals here at school.
Oh, okay.
Sometimes I have to test things out, right? I don't have time to do it here, so I just take some. Okay. Okay, here we go. Lycopodium powder. Heat source.
I wonder if it's,
Oh. Ta-da.
95. Let's go circle and pass.
Look how dangerous this is.
honestly, you could use it to light a fire, just like you're camping. Or
Cute
do
little
that.
candle, right? Cute.
Does it smell
Anyone
nice?
questioning why it's like has these warning labels on it?
Well,
I mean, it is flammable, right?
yeah.
But
so is like everything.
but in that case, it seems like everything should have a warning label, right? Okay, I'm gonna put this out. Now, I'm gonna do the same thing,
Everything is California.
but I'm gonna change the form of how the lycopodium is, okay?
Yeah, in California, we bought some chairs, and they came with the label that
Oh,
said
gee, just
that the
opposite.
sawdust from the factories that could still be on the chairs is known to cause cancer. We were just like, this is ridiculous.
Whoa.
Well, like, they don't, right? Because
everything does.
Disneyland causes cancer. It's ridiculous. There's a sign outside Disneyland that says, warning, Disneyland causes cancer.
Well, it's because like California has some law, right?
Yeah,
That you
it's
have to like
Proposition something,
Like-
60 something.
possible carcinogens, but like everything is a
Yeah.
carcinogen.
It's so funny.
Okay, so notice I'm not adding anything new. I'm just changing the physical state of my lycopodium, okay? Everybody ready?
Whoa, that was cool.
It's
What?
What?
Nice, let's make some napalm.
No.
Do it again, do it again, do it again.
Close.
Do it again, do it again. That was so cool.
Okay, I'll do it again.
Flamethrower. Oh man.
Wait, that was amazing.
It's not dangerous. I mean, don't eat it. But I'm not like I don't need to go poison control.
The fire, like,
Wait.
Ugh. It's just like you remember when I showed you guys this powder before? This is the one where we dipped our finger in it.
Oh, yeah.
Oh,
So it like doesn't dissolve in your mouth, right?
Oh,
That's
yeah.
It feels like there's like
that.
sand in my mouth.
Oh, there's a nice smell.
Did you You just got it?
Yeah.
Yeah, me too.
It kind of smells like hot dogs, not gonna lie.
Oh, it kind of does.
Yeah?
It smells like a barbecue.
Yeah, exactly.
Oh, yeah.
It does.
It does?
Like barbecuing hot dogs. Yeah.
Yeah, it does.
Oh, it's.
Oh, now it does.
Oh my gosh, this is a nice smell. Wait, is this what the candles smell like? Because now I'm This is awesome.
My mask messed with my peripheral, so I didn't see that it hadn't slid down the tube. Okay, everyone ready?
Honestly,
Slow-mo looks really cool, by the way.
Oh, are you doing it?
Oh, yeah. Oh,
Yeah.
slow-mo.
My camera's really bad sometimes.
Wait, no.
Wait, are you filming vertically? That's a sin. You can't do
Yeah,
that.
it's VBS.
Thank you.
Huh?
Filming
Vertical
vertically.
video syndrome.
Yeah, it's illegal.
Whoa.
It should be anyways.
Okay, everybody ready?
Yeah.
Oh my.
Wow.
Okay, so what's going on here? Why, same thing, right? Why was it so different
I have no
through this?
idea.
Isaac?
Add more air to react with.
Good. So in a sense, the same amount of air, but the space in which it could react, right? In this pile right here, what molecules can react? Only the ones on top, right?
Whoa.
When you spread it out, all of a sudden now they all can hit an oxygen in the air, right? Because you need oxygen to burn. So on and so forth. So if you want to kind of, it's not said explicitly,
I kind of love this. This is awesome.
but if you want to make a side note, surface, or I guess it is right here, surface area is key. If you can increase the surface area, you get more collisions, faster reactions. That's why often like we'll grind things up into a powder before we dump them in.
Is that why the bad guys spread out the gunpowder in cartoons when they light it instead of just
Yeah.
like, okay.
I don't know, but I thought that's because they like
when
make
it's
like a trail.
Yeah, when it's
Yeah.
trail, you know what I'm talking about? They don't clump it together, it's nice and just flat, you know?
Like a nice little bit. So. Okay, second thing, we can control concentration, meaning the molarity of it. A higher molarity obviously is going to react faster because there's more stuff in there, right? So we'll actually do a lab next week, I think it falls, where we'll test a reaction with hydrochloric acid, and we'll do a 1 molar, 2 molar, 4 molar, and 6 molar to see that increase in the rate as you go to a higher concentration. So another thing we can control is temperature. Temperature of reactions, if you heat something up, it's typically going to react faster because what are the molecules doing? They're moving faster, right? Faster they're moving, higher energy, more successful collisions. This is really why we put, I mean, you've never thought about it before, but that's why you put food in the refrigerator. It's because the
Whoa.
colder temperature slows down the reactions with bacteria or other things, so it stays fresh longer.
That's cool. Wait, then what does salt do? Because they'll like put salt, they used to just like put salt in their meats and stuff to store them
It
longer.
dehydrates it.
Oh, is
Water
that what it
helps
is?
bacteria
Yeah.
survive.
Yeah, so if you have less water, because water, bacteria grows well with water, right? So. Okay, and then the last one, which I'll show you another demo of, is a catalyst.
That's the name of the book about Grandma Tarkin.
Catalyst?
Yeah. Grandma Tarkin.
Grandma?
Grand Moff Tarkin, Star Wars guy who made
Oh.
Death Star.
I thought you said grandma.
No.
I did too.
It's like a book about a grandma?
Yeah. It's kind of
Yeah, that blue guy.
Yeah.
Huh?
Blue guy.
No, not that's Thrawn.
Oh, yeah.
Grand Moff Tarkin's the guy they CG'd in Rogue One and looked kind of really bad. You know what I'm talking about?
Oh, it is in the new Hope too.
Okay, so we'll talk more about catalysts throughout the unit. For now,
He's dead now. Well, he's dead in real life too.
here's the main things I want you to get from it.
He's dead.
I picked
He's dead in fucking lives.
Okay, give me your attention here, everybody. So a catalyst is a substance you add to a reaction, and it makes the reaction go faster. The key thing, though, of definition is the catalyst is not part of the reaction. The reaction would happen without it. but it speeds it up, and the cool thing is it can be used again. In biology, you talk about these things called enzymes.
Oh, yeah.
An enzyme is a biological catalyst because what do they do for us?
Digest.
Break down our
Yeah. If we didn't have
Uh,
enzymes in our body, food would like never digest,
I'm so hungry right
right? And like, sadly, some people are lacking certain enzymes, like if you're lactose intolerant.
Oh, man.
If you're lactose intolerant, you don't have the enzyme lactase, which means you can't digest lactose, right? Cool thing is we in our science world, you can literally take a pill of lactase if you're lactose intolerant, and then you're good.
Wait, really?
Now you have to take it like every day, yeah. So I'm like partially, like I'm kind of lactose intolerant, like it just doesn't sit well with me.
Yes,
So if I eat a pill before I like have some ice cream, I'm fine.
lactose sensitive.
Yeah, there you go.
What is lactose
But it's kind of cool in the sense of that's what it means. So in chemistry, they work in a similar sense of that it just makes the process go faster, okay? So the reaction I'm going to show you is hydrogen peroxide, which is H2O2. Okay, so this, you might be familiar with it. You might have it at your house in a bottle that looks like this. Everyone familiar with this?
Oh, it's like
Yeah.
that?
Wait,
What does your mom do with this?
Pours it on my cup.
Yes.
Oh, it bubbles up in it.
Yeah.
It's kind of sick, actually.
You pour it on your cuts and it bubbles. Doesn't, I mean, some say it kind of stings a little bit, but it cleans them out, right?
More fun than-
Okay. This is the same thing, it's just a higher concentrated solution. So this is a 3% solution. This is a 30% solution.
That's a little bit more.
So a little bit more. This you do not want to pour on your cuts because it corrodes your skin that's not cut.
Oh, that's sick.
So yeah, you don't want to put it on cuts.
All right, nose goes.
Anyone have a paper cut there? Volunteer. So any guesses of why both of these are stored in brown bottles? Any thoughts of why they do that?
The light or something is absorbed.
Yeah, so this chemical H2O2 decomposes when exposed to light.
What?
So when light hits it, it breaks down into water and oxygen. Yeah.
So like when they make it, like in the factory or wherever,
Yeah.
is it dark?
I don't know,
It's
Evan.
made in Pennsylvania by a bunch of vampires.
I don't know. That's a good question.
They're just like.
It's just a bunch of vampires in a factory.
Yeah, Kimberly.
So if you poured this out into like a container and left it in the sun, would you be left with water that you could drink?
Hypothetically,
Ah.
you shouldn't drink this. That's why actually they have expiration dates on the bottles. It's because even for the bottles, they're not perfect at keeping all light out. So over time, like let's see what this one says. Oh, this one's already expired. Holy cow! What year are we in?
2021.
This expired 6 years ago.
Drink it, drink it, drink it.
Well,
It's
it's
just
kind of
water in
interesting.
it.
So that's why if your mom does have a long one and you pour it, it won't like be as effective, is
Anybody
because
have a cut?
what's in this bottle, maybe not all water, right? But it's mostly water. That's also probably why it feels quite pressurized right now. It's because it's also making oxygen gas.
It looks like it's gonna.
Can you see it's kind of bulging
Yeah.
a little bit? That's why when I buy the high concentrated one, the 30%, when it comes to me, it's only filled up about this much. Because it's so concentrated, if this one breaks down, it could cause the bottle to explode.
They weren't just trying to scam you like a
No,
crack
yeah, I'll get
shit.
shit back. No, right? I'll just show you, they used to send it, I'll maybe grab one, in these cool like accordion bottles that can expand so they don't explode, right?
I love the accordion.
Okay, so I'm gonna pour it into this
My
flask.
dad has an accordion.
Safety first.
He's pretty good at it.
Okay, and we can watch it.
Fire first. Yeah,
Basically, you should put it on.
in the words of Vin Diesel, family first. So I guess safety comes
Drink it.
second.
Okay, everyone look closely.
Third?
Can
Okay.
you see it happening?
Does anybody still smell hot dogs? I'm still there. I'm getting hungry.
Yeah, me too.
So it's being exposed to light, so it does decompose. But this reaction is quite slow.
Oh.
So I'm gonna add a catalyst to speed it up. what I want you once again to recognize is it doesn't need the catalyst to happen. The catalyst is just going to save us like 5 years.
Oh.
Okay?
Nice.
So I don't know if you guys want to hang out that long with me.
Wait, I want to watch the real thing.
Now, the other thing that's significant about a catalyst, everybody, okay, is catalysts are very budget friendly because it doesn't get used up in the reaction. So after it's done, I can get this back out and use it again and again and again and again. There's actually, I'd say, a pretty big industry for chemical engineers to make catalysts for certain things. Because if you are producing a pharmaceutical drug, well, let's say the vaccine, and you could get a catalyst to make the vaccine faster, right? That's normally something people want to do. So, okay, here we go.
I would like to go for
I'm so sick.
that. Whoa!
Choo-choo.
I wonder what this tastes like.
Dude, that
I'm
catalyst.
glad I
So, once again, water, oxygen, we made our cloud, right?
Oh, you can't see it after the light. Does anybody else have that? You can see the
What's
projector
the
light, and
Yeah.
it's like a defined
It's
line.
manganese dioxide.
Can I breathe it, or should I?
Now, in terms of, can you breathe it? What is it?
Oh, okay, that's true.
You good? Totally good.
It just gets kind of humid.
When you use a catalyst, there's typically, you place it on top of the arrow if you use one, because it's not a reactant, it's not a product, it just helped it go faster. But once again, notice you can see it's quite, we'll learn more about this, but it's an exothermic reaction, so it produces a lot of heat, so the flask is quite warm. So I'm not going to hold it right now. But you can see the liquid down here is black from the catalyst. If I got some filter paper, I could pour it in and catch that black powder, dry it, and then put it back in my bottle, right? So once again, we'll talk a lot about catalysts throughout the unit of kind of like how does it make it go faster, so on and so forth. But any questions for now?
Can we do it
I think
again?
go faster.
Can we do it again? Yeah, Kimberly.
What does it do to make it go faster without like reacting or anything?
So there's a lot of different types of catalysts in how they are like what helps them go faster. So the simple answer for now, and then we'll get into more detail, is they provide some way to make the collisions be more successful. Whether that means it makes it so it requires less energy to do it, or it helps possibly with the orientation. Like enzymes work a lot that way because they're like a lock and key idea where it kind of holds it in place, and so it only can collide a certain way. But yeah, they just do something to help create more successful collisions so it can just go faster. But stay tuned for more. But good question. Any other questions for now? Yeah, Max.
Could there be an enzyme that does the opposite of what you want it to, so it holds it in the wrong direction?
Yes. What are they called?
Oh, where they slow it down?
Inhibitors, I think. So I think an inhibitor does the opposite
Not
of where it
probably.
slows the reaction down because it prevents it from linking up with the enzyme. So, yeah, good
Is
question.
there any of those in your stomach?
Ooh, like naturally?
Yeah,
I don't know.
because that could be a really good, like, business idea, because if you could have like a pill that would get rid of the enzymes and make it hard for you to digest, if there were any,
Yeah.
then people would be like super digested.
Yeah.
I don't know.
Oh my God.
Yeah, I don't know if I'm not sure if there's like things that we have that inhibit digestion, or if all of our problems with digestion are just we don't have enough enzymes of certain things or something. But I don't know. We'll have to go team up with the
Max, you get on that.
biology teachers. That's biochem right there. So, good question.
And Max,
Yeah.
if you
Okay,
make bank
this
on
is
this,
a
I'll
little
get
off
10%.
topic, it's been fun.
Okay.
So you know when you like
Oh,
blow out
really?
a certain
Okay.
way it's cold air, and when you blow out a different way it's hot air? So how does that happen? Because it's like how fast they're moving, right? So how do we get them to move faster sometimes but not the other time?
I have no idea. I've never even thought of that before, Kimberly.
It's so weird, isn't it? that's what temperature is.
Yes.
Yes.
So how do we control that? That's insane.
Oh wait, yeah,
You
what?
get what I'm saying?
Yeah.
Yeah, because if you like go, it's like warm.
It's hot.
But if you go, you can't see my mouth. Everyone knows what I'm doing, right? Like,
Yeah.
but if you blow out like a birthday candle, it's not.
When you go, hot is warmer.
And you can keep them the same speed, like you don't have to do it fast or slow.
Yeah, and there's no way our force doesn't influence the actual speed of molecules. Do you know what I mean?
Right.
Huh?
Yeah, cause you could
I'm
do,
stumped.
you could do the, like,
Yeah.
birthday candle slowly and it's still like cold,
Yeah.
or
Yeah.
not cold.
I'll come back. I'll ponder that.
Because like you're pushing it out faster and it like disperses more.
Well, and the tricky thing is hot and cold are just relative terms, right?
Right.
Like things feel hot, but they, you know what I mean? So it's like, that's the other interesting thing is when we get to our next unit about thermochemistry, maybe we'll bring that up again. Because yeah, hot and cold are just relative.
That's true.
Like cold doesn't exist in the world of science.
Yeah.
Oh yeah, because heat transfer goes one way.
Yeah, like you don't,
Yeah.
cold isn't something that's actually measured, it's just a lack of heat.
Right.
It could be like the acetone, where just like
Wait.
goes way faster.
Yeah, that's kind of what I was thinking, because like the acetone, right, like when we did that, how it felt cold,
Yeah.
but it like, it's not cold, it just felt cold to us. But why, it still does feel different though, that is interesting, like why does one way feel hot to my hand and one way feel cool to my hand? I don't know. That's a good question. You might keep me awake.
It does. I'm
What
serious.
up, Visa lies awake at night wondering why is my head so
Just bloodshot.
I'm just gonna be breathing in my bed. Then it will come to me. Actually, I've been listening to an interesting podcast thing all about sleep and the power of sleep in terms of like coming up with ideas. And he told a cool story of how, oh shoot, I think it was, oh my gosh, now I can't even think.
JFK.
Benjamin.
Franklin.
There we go. Is he the light bulb guy?
Yeah.
Thomas Edison. No, but I think it was Benjamin Franklin. I think he's one of those two.
Franklin.
With, like,
Yeah,
human
yeah,
eyes,
hi.
right?
Okay, one of those two, because they're both like inventors, right? I think
Yeah.
there's probably Edison.
Yeah.
I don't know. Don't
Well,
quote me on the person.
It was a scientist dude.
Some scientist, famous guy, would
Franklin.
literally, because there's like a certain point in your sleep where like your brain like takes everything you've learned from the day and starts like
Yeah.
putting it together, right, in REM sleep. And so he would very strategically like work on a problem and then take a nap, and he would set it up in a way where he would hold a ball in his hand,
Oh.
okay?
Oh, I've heard.
And he'd put a metal pan underneath it, okay? Because when you start transitioning out of REM into deep sleep, your muscles relax, okay? So he would take a nap with this ball in his hand and a little pan underneath it, so that when his muscles relaxed, the ball would roll, hit the pan, and wake him up. So he'd wake up right after REM, and then he'd write down all his ideas.
Oh my gosh.
Isn't that crazy? And he'd like do this all the time. I'm like, man, I don't know if I have that much like, I just like sleeping. So. I'd rather not. But, you know, if you're ever stuck on a problem, take a nap, you know. Great question. I have no idea.
I'll think of more for you.
Okay. We'll add that to, I haven't ever pulled it out this year. Last year we had a chemistry jar
Oh,
of like questions to talk about like after the AP test of things that we're just still not sure about. So I'll find the jar and we'll pull it out. and that can be
Below
questions.
0
So,
Kelvin.
okay, back to the math side of things. What we're gonna look at now, so what we looked at before was like a rate, molarity per second. Okay? What we're gonna look at now is how we can write a mathematical equation that can be used under any situation. Because the benefit of that is you don't have to keep experimenting. Experimenting is great up to a point, but then it kind of gets repetitive to just have to do the thing over and over and over again. If you can just plug numbers into a mathematical equation, it's cost effective and time efficient, okay? So that is what is known as a rate law. A rate law is a chemical expression or a mathematical expression that helps you know how rate is influenced by the reactants. Okay, first off, this is important to recognize that the rate law is only based on the reactants. We do not include products in the rate law. just because we're focused on, okay, how does A affect the rate? How does B affect the rate? Okay, so A and B are reactants. M and N are exponents known as rate orders. They help you know to what extent does A affect it, or to what extent is B affect it. K right here is known as the rate constant. And this is the piece to the math that brings in temperature.
Okay.
Little k, yep. So if you do an experiment under the same temperature, K won't change. That's why it's considered a constant. But if you change the temperature, K will change in numerical value. So what we're going to learn and then practice today is how to write a rate law and then how to use it to find information about our equation. Okay? So let's write a few things about M and N here. Okay, so M and N are the rate order. And they, once again, help you understand how things are affected. There's 3 types of rate orders we'll see in this class, or at least you'll determine in this class. There are more outside of that. It's just a little bit past our, I guess, what we're going for. So we have 0 order, which means you doubled the concentration, but the reaction didn't get faster. That's considered 0 order. It doesn't affect it, right? You can dump as much as you want in. Doesn't make it go any faster. Okay? We then have first order. Okay? Which means that when the concentration doubles, the reaction also doubles. Or if the concentration triples, the reaction triples. It's a 1-to-1 same change. Second order means that when the concentration doubles, the rate actually quadruples. Yeah.
So I've heard of this thing where if you get too much products, it will slow down the reaction. Does that have anything to do with this? Like when, let's say, okay, you're in a bubble bath. You put in too much bubble bath. You get to a point where there's too much bubble bath to water, so you stop getting bubbles.
Good question. It would kind of be related to the rate. I'm trying to think of it, that would be in a sense the
It
order.
would slow down the rate, wouldn't it?
Oh, yeah. So that would be exactly it, because what is happening is you're getting a lower concentration of water. So when the water concentration goes down, the rate goes down. Yeah, good analogy. So here's some examples of just some equations and what their rate laws look like. Okay, so here's the equation, here's the rate law. Okay, the biggest thing that you need to understand and why I put 5 exclamation points is they are determined experimentally. Okay, you can't look at a balanced equation and write a rate law. Now sometimes it may look very matchy, right? Like this bottom one here has H2I2, and then here's the rate law. Okay, so sometimes it looks like it just matches exactly, but it only can be determined through experimental means. For example, if you look at the first one, you'll notice, I don't know where my stick went. Oh, here it is. Okay, notice that there's a 2 right here in front of this reactant, and that 2 didn't show up in the rate law. Okay, so just kind of be aware of that. And then the biggest thing is K, once again, is temperature dependent. Okay, if temperature changes, K will change. Or if K changed, that means temperature changed. It's the only way that it affects it. The units of K are a little unique, and we'll see that as we do this next problem. It doesn't have a set unit. Yeah, Evan?
So how do we get the unit of N, which is like the top right corner, like, and that one is 0.5 again?
So how is that found?
Yeah.
Let's show you.
Okay.
Good question. That was like perfect leading. So the way to find the rate order is you have to go off experimental data. What we're going to do is we're going to look at the data and see what did we change and what was the result. Okay? With our data table here, a few things to note. Oh, that's thing right in the awkward spot. Okay, we'll make this work. Okay, we control concentrations. I go in the lab, I pick which concentration I use, right? So this is like chosen by the experimenter, right? I control these. the rate is the result. This is what is affected when I change the concentrations. So I would start to find my rate law, so that's our question here. I'm going to write the generic form. So rate equals K. In this reaction, we have NH4 plus and NO2 minus. Question is, we want to know what is M and what is N. What are their exponents? Once again, keep in mind, if a problem says, find the rate law, your answer should be a whole equation. It's not a number, right? It's a whole equation. Okay, so what we want to do is we want to find how does NH4 affect the rate. So I'm starting by focusing on one, which means I want to keep the other one constant. Now, it doesn't matter which experiment you pick. This one, in a sense, gives us lots of options. We just want to pick one where this changes and that stayed the same. So I'm just going to write a note of what I'm doing. So I'm picking 2 trials where NH4 changes, but NO2 does not. Why do I want to keep one thing the same when I'm trying to compare? Yeah, otherwise it can get really messy of like what's actually affecting the change, right? It's like when you do a chemical experiment, you can't change everything if you're trying to track what caused the change. Okay, anyone have a choice of 2 trials you want to compare? Throw out 2 numbers. Where it falls this.
2 and 3.
2 and 3? Perfect. Okay, 2 and 3. So what we see here are, we see this stays the same. How did this change? It doubles. Times 2. When I doubled the concentration of NH4, what was the result in the change of rate? Also doubled.
Oh,
Okay, which tells me that M is first order.
Oh my gosh.
Because the concentration doubled, the rate doubled, so it's a first order relationship.
Okay.
Good so far? Okay, so now to find N, the opposite. So someone pick 2 trials for us. Which ones look good?
4 and 5.
4 and 5, those look good to me. Okay, so 4 and 5, this stays the same. Okay, the concentration doubled and the rate also doubles. Which tells me that N is
Oh my gosh, they're all first order. This is bad. Bad news.
So then your answer for the rate law would be rate equals K NH4 plus NO2 minus. Because anything, you don't really have to put the power of 1. If you want to, you can. Like if it makes you feel better.
First.
But
oh, that makes sense now.
Oh wait, so if this is 0, we put it at 0?
yes, or you don't have to even write it.
We use 0 order.
Because anything to the 0 power mathematically goes to 1, right? Okay, questions how I found our exponents. M and N. Okay, before we do the next step, I actually want to have you practice this, because it's best to practice right after while it's fresh. So turn your paper to the next page, and with your table buddy, and this data, find me the rate law for A and B. Ready, set, go.
Okay. So the things are first, just A and
final answer, write it in that box below, and then raise your hand and I'll come check it.
Is after B stays constant. When that stays the same.
Okay, so then that's first.
Nothing happens. So like,
Oh,
these two, nothing happens.
so we know
So do you want to be
A
zero
is
So I always just
do that and then
to like,
and then
or it does. You can always compare either directions. Whenever I'm comparing, I always compare big to little. Is to tell. But so like if you wanted to compare this one to this one, I would just look 3 to 2 instead of 2 to 3.
so
That makes sense.
it would be zero.
Oh, so we're doing this one.
Once again, your final answer should be an equation.
This one
Oh, okay.
So I guess and then one is three. Three is A doubles.
So B just becomes 1 and then B
And
Once you have an answer, raise your hand and I'll come check it.
So whenever A is double, the reaction.
That makes sense.
Yes.
Let's go.
They're like the same.
So A.
They don't say the same.
So we're trying to find N for A. First, we have to do where.
Yes, good. That's nice.
No.
I don't know, how do you do, how do you find what A is?
It's my face for you.
This is A when this is double. Or just, it would be zero because when this is the same,
So you can just.
this one double.
Well, there's not one that B is the
Yeah.
same.
Oh, that's what you just added.
Oh, you see that?
So
Oh,
then-
I didn't know that.
They're just trials, right? So it's like you can compare any. Normally I go side by side because it makes life easier. But you can compare any direction, any 2 trials you want.
It was a bad start, right?
Good, Isaac?
Hey, but then if you look at the initial one,
I don't know if I checked yours already. Walking in circles.
Square.
that make it, where's the lady?
Oh, that's not their order. No, you
There is no third order.
Second order said that IOU.
That's never how this went down. You should have heard that.
Oh, yeah,
There is no third order. This is only the first order.
the second, yeah, we're pros, man.
Okay, you should have, I think I checked most. But your answer should be rate equals K, A to second order, and then B is 0 order. So you could write it like that, or you could just take out the B. Okay, questions so far. This is one of the things you'll be doing on worksheet 5.2. Is given data tables, compare. Few notes on that. Number 1 is if mathematically, these are like easy to see, like, oh, I can see that doubles or not. If you can't mathematically quite tell, you can always plug them into your calculator just as a fraction, right? So if you're not sure, is this doubling, quadrupling, tripling, or whatever, just take the bigger one and divide it by the smaller one, and that will give you how much it's changing by. So, okay, going back to the other one we started with, the next step is to then determine the numerical value for K. Okay, because K is a constant and it has a number associated with it for the given temperature. So, to find the value for K,
Bless you.
we are going to plug in any set of data. So pick your favorite trial number because it doesn't matter. Okay, I'll pick trial number 2.
Oh,
Oh, do you have another
4
favorite?
was my favorite, but
Let's
that's
do,
fine.
we can do 4.
Oh, really?
Yeah.
You did that?
Yeah.
Oh, you're so
Okay, so I'm just plugging this into my equation I just came up with. So the rate for trial 4 was 10.8 times 10 to the negative 7 molarity per second. So I plugged in the rate. Equals, I'm trying to find K. So leave that as a variable. Concentration of NH4 under those conditions was 0.2. And the concentration of our other one was 0.0202. Now make sure when you plug it into the rate law, if these were second order, those would be being squared right now.
Oh.
So don't lose your orders when you start plugging things in. Okay?
If it was 0 order, would that just mean it's just 1?
Yeah, so if it's 0 order, you technically don't have to even plug anything in, right?
Okay, just all these 1.
Yep. So then, rearrange solving for K. So I'm going to get K by itself. So we're going to have 10.8 times 10 to the negative 7 molarity per second over, I'm just showing you like what I plug into my calculator. I got 2.7 times 10 to the negative 4. I plug that in. Now, the units are extremely important. Whenever I've seen this type of problem on a first response section, it's always been a point for the units of K, because it's not a set unit. Like molarity is always moles per liter. Rate is always molarity per second. But K, its units change depending on the orders of the reaction. So looking over here for units, this is molarity per second, and then I have molarity and molarity on the bottom. So the molarity on top can cancel with one of the molarities on the bottom.
Second polarity.
Okay, so then it's kind of a weird unit, but you have seconds, like per second times molarity, because second and molarity are both on the bottom.
Oh, what the heck?
Or the other way you can write it, am I disappearing off my camera screen if I write over here?
You're fine.
I'm okay. So you can also write it as, so there's our number, inverse seconds, inverse molarity.
That's so gross.
Yeah. So, but either one works. Questions on finding what's called the magnitude of K. Magnitude referring to its numerical value. Okay, then the last piece to the problems that you'll see on 5.2 is then they could give you a new set of data, and without having to do an experiment, you can then just plug it in to the rate law. So for example, this problem could say, I think it did actually on part C, if you look there at the bottom, it says, what is the rate when NH4 equals 0.1 and NO2 equals 0.1? So we would just plug in 0.1, 0.1, plug in your K, and find your rate. Okay? Any questions there for now? This is kind of the main thing you'll be practicing on the homework tonight, is interpreting these charts of data to get a rate law. So let me pass that out. There is a little bit of reading tonight too, so if you do come across, or if you do still have questions or come across questions, you can get those posted. And then there's just one 5-point quiz on AP Classroom. Oh.
Thank you.
Yep.